let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders like morning mist rising from a quiet lake. Take a slow, gentle breath, feeling the air move through you, and as you exhale, let any lingering tension drift away, dissolving into the peaceful evening air. Tonight, we're embarking on a journey through the cosmos, but not one that requires any effort from you. Just close your eyes if you'd like, or let them rest softly on a distant point, and allow this story to unfold around you like a warm blanket on a cool night. We are going to explore something remarkable together, the strange and beautiful phenomena that populate our universe. Things so peculiar and unexpected that they challenge everything we think we understand about reality. But don't worry about remembering every detail or grasping every concept. Simply let the words wash over you, painting pictures in your mind of cosmic wonders that stretch beyond imagination. Black holes aren't the strangest things. When most people think about the weirdest objects in space, black holes immediately come to mind, and it's easy to understand why. These gravitational monsters capture our imagination like nothing else. Regions of space-time where gravity becomes so overwhelmingly powerful that not even light itself can escape their pull. They're the universe's ultimate one-way doors, boundaries beyond which the normal rules of physics seem to break down completely. Inside a black hole, space and time trade places, creating a reality so alien that our minds struggle to comprehend it. If you were unfortunate enough to fall toward one, the difference in gravitational force between your head and your feet would stretch you like taffy in a process scientists rather grimly call spaghettification. Meanwhile, to an outside observer, you'd appear to slow down and freeze at the event horizon, your image fading to red as time itself dilates around you. These objects warp the very fabric of reality, creating whirlpools in space-time that can spin at nearly the speed of light. But here's the remarkable truth that we're going to explore together tonight. As strange and wonderful as black holes are, as much as they've captured the public imagination and transformed our understanding of gravity and space-time, they're actually not even close to being the strangest things in the universe. In fact, when you really dive into the cosmic catalog of bizarre phenomena, black holes start to look almost conventional, almost boring by comparison. They're strange, yes, but they're also well understood, at least in broad strokes. We can predict them with Einstein's equations. We can observe them through their effects on nearby stars and gas. We've even captured images of their event horizons using arrays of telescopes spanning the entire Earth. Black holes, for all their weirdness, follow rules. They behave in ways we can model and understand, even if the mathematics gets complicated. They're the cosmic equivalent of a familiar mystery, something that once seemed impossible but has now become part of our accepted view of reality. The universe, however, is filled with phenomena that make black holes look positively mundane. There are objects and forces out there that don't just bend the rules of physics but seem to rewrite them entirely. There are mysteries so profound that we don't even know what questions to ask about them yet. There are structures and behaviors in space that challenge not just our mathematical models but our fundamental assumptions about what reality can even be. Some of these phenomena were predicted by theory and later discovered, their existence confirming our most abstract mathematical ideas. Others were stumbled upon by accident, caught in the data from telescopes and satellites, surprises that forced physicists to go back to the drawing board and rethink everything they thought they knew. and still others remain purely theoretical, mathematical possibilities that might exist somewhere in the cosmos, waiting to be found, or might be forever beyond our ability to detect, ghosts in the equations that haunt the boundaries of our knowledge. Tonight, as you relax and let your breathing slow, we're going to journey through some of these cosmic oddities together. We'll encounter magnetic fields so powerful they could distort the very atoms in your body from thousands of miles away. We'll explore theoretical objects that reject the fundamental arrow of time itself, places where cause and effect might run backward. We'll discover invisible scaffolding that holds galaxies together, made of something we can't see, can't touch, and don't understand, yet know must exist because without it, the universe would literally fall apart. We'll investigate flashes of energy so bright they outshine entire galaxies for a fraction of a second. Bursts of radio waves that cross billions of light years of space and then vanish, without explanation. We'll contemplate cracks in the fabric of reality itself, theoretical defects in space-time left over from the universe's first moments, thinner than a proton but heavier than mountains, stretching from one horizon to the other. Each of these phenomena is stranger in its own way than any black hole. Each one challenges our understanding and expands the boundaries of what we know is possible. So, breathe deeply. Let your muscles relax and prepare yourself for a tour of the truly strange corners of our cosmos. Dark matter, the invisible scaffold. Let's begin with perhaps the most profound mystery in all of modern cosmology. Something so fundamental and yet so utterly baffling that it represents one of the greatest embarrassments in physics. That's not my description, by the way. That's how Timothy Kovacci, a physicist at Northwestern University, describes it. We're talking about dark matter, the invisible substance that makes up roughly 27% of the total mass-energy content of the universe. To put that in perspective, everything you can see, everything you've ever touched, every star in the night sky, every planet, every galaxy, every nebula, every particle of dust drifting through the cosmic void, all of that together, all of what we call normal or baryonic matter, accounts for a mere 5% of the universe. The rest is split between dark matter at 27% and an even more mysterious thing called dark energy at roughly 68%. But let's focus on dark matter for now, because it's strange in a very particular and unsettling way. The story of dark matter begins in 1933, when a Swiss astronomer named Fritz Zwicky was studying something called the Coma Cluster, a collection of over 1,000 galaxies bound together by their mutual gravity, located about 320 million light-years from Earth. Zwicky was measuring how fast the galaxies in this cluster were moving, and he noticed something deeply wrong. The galaxies were racing around far too quickly. According to the laws of physics as understood at the time, based on the amount of visible matter in the cluster, these galaxies should have been moving much more slowly. At their observed speeds, they should have escaped the cluster's gravitational pull entirely, flying off into the cosmic void like marbles scattered across a floor. But they weren't escaping. They were staying together, bound by some invisible hand. Zwicky calculated that there must be about 400 times more mass in the cluster than could be accounted for by all the visible stars and gas. He called this unseen mass dunkle Materie, German for dark matter, because it must be there, exerting gravitational influence, but it doesn't emit, absorb, or reflect any light. For decades, Zwicky's observation was regarded as interesting but not conclusive. Maybe his calculations were wrong. Maybe there was some error in his measurements. Maybe the laws of gravity worked differently on cosmic scales than we thought. But then, in the 1970s, an astronomer named Vera Rubin conducted a series of groundbreaking observations that would confirm and extend Zwicky's findings in a way that could no longer be ignored. Rubin studied the rotation curves of spiral galaxies, measuring how fast stars orbit around their galactic centers at different distances. In our solar system, planets farther from the Sun orbit more slowly than those closer in, a relationship that follows directly from Newton's laws of gravity and Kepler's laws of planetary motion. Mercury races around the Sun in just 88 days, while distant Neptune takes 165 Earth years to complete a single orbit. Everyone expected galaxies to work the same way, with stars in the outer regions moving more slowly than those near the center. But that's not what Rubin found. Instead, she discovered that stars in the outer reaches of galaxies were moving just as fast as those closer to the center, sometimes even faster. This observation, confirmed in galaxy after galaxy, was profoundly strange. According to the visible matter alone, those outer stars should have been flung off into intergalactic space long ago. The only way to explain their high velocities was to assume that galaxies are embedded in enormous halos of invisible matter. Matter that doesn't shine or emit radiation, but whose gravity keeps the outer stars bound to their galaxies. This dark matter halo had to extend far beyond the visible disk of stars, creating a gravitational scaffolding that holds galaxies together. Without it, galaxies would simply disintegrate, their stars scattering across the universe like dandelion seeds in the wind. Since those early discoveries, evidence for dark matter has accumulated from multiple independent lines of observation, each one confirming its existence through different physical effects. When we look at galaxy clusters through powerful telescopes, we can see how they bend light from more distant galaxies through a process called gravitational lensing. Massive objects warp spacetime, and light traveling through warped spacetime follows curved paths. By measuring these distortions, astronomers can map the distribution of mass in the cluster, and every time they do this, they find far more mass than can be accounted for by visible matter. The maps of gravitational lensing show vast pools of dark matter throughout these clusters, invisible but undeniably there, revealed only by its gravitational influence. In some cases, like the famous bullet cluster, we can even see where the dark matter and normal matter have separated during a collision between galaxy clusters, with the dark matter passing through essentially unimpeded, while the normal matter, made of gas that can collide and slow down, lags behind. Perhaps the most striking evidence comes from observations of the cosmic microwave background, the afterglow of the Big Bang, a radiation that has been traveling through space for over 13 billion years. This radiation carries an imprint of the conditions in the early universe, tiny variations in temperature that correspond to regions of slightly higher and lower density. These variations are the seeds of all future structure in the universe, the places where matter would eventually clump together under gravity to form galaxies and clusters. By carefully analyzing the pattern of these temperature fluctuations, cosmologists can determine not just that dark matter exists, but how much of it there is. The measurements are remarkably precise, telling us that dark matter makes up about 27% of the universe's total mass energy content, or about 85% of all matter. That means for every atom of normal matter in the universe, there are roughly 5.5 times as much dark matter, invisible and unknown. But here's where dark matter becomes truly strange. We know it's there. We can measure its gravitational effects with exquisite precision. We can map its distribution throughout the universe. We can see how it influenced the formation of structure in the early cosmos. We can determine how much of it there is. But we have absolutely no idea what it actually is. And that's the embarrassing part that physicists like Cavacci were talking about. We understand normal matter extraordinarily well. We know it's made of atoms, which are made of protons, neutrons, and electrons, which in turn are made of quarks and leptons. We've built an incredibly successful theory called the Standard Model that describes how all these particles interact with each other through various forces. We can predict the behavior of matter with stunning accuracy. But dark matter doesn't fit into this framework. It doesn't interact with electromagnetic radiation, which is why it's invisible. It doesn't interact with the strong nuclear force or the weak nuclear force, as far as we can tell. The only way it makes its presence known is through gravity, and gravity alone doesn't tell us much about what something actually is. Physicists have proposed numerous candidates for what dark matter particles might be, each with its own theoretical backing and predicted properties. One of the most popular ideas for decades has been something called WIMPs, which stands for Weakly Interacting Massive Particles. These would be particles that have mass, creating gravitational effects, but interact only very rarely with normal matter through the weak nuclear force. Experiments deep underground, shielded from cosmic rays and other interference, have been searching for WIMPs for years, trying to catch the incredibly rare event of a WIMP colliding with an atomic nucleus. The most sensitive of these detectors, the LUX Zeppelin experiment, uses 7 tons of liquid xenon and is buried nearly a mile underground in South Dakota. In 2024, it released results that were nearly 5 times more sensitive than previous searches and found nothing. No evidence of WIMPs above a certain mass range. The experiment will continue running, pushing its sensitivity even further. But after decades of searching, WIMPs are beginning to look less likely as the answer. Another candidate is something called axions, hypothetical particles that would be much lighter than WIMPs but extraordinarily abundant. Axions were originally proposed to solve a completely different problem in particle physics, but they happen to have properties that make them excellent dark matter candidates. Unlike WIMPs, which would interact rarely but with measurable energy, axions would barely interact with normal matter at all. Instead, experiments search for them by looking for their effects on electromagnetic fields. One experiment, called the Broadband Reflector Experiment for Axion Detection, or BRED, uses a specially designed antenna dish to search for extremely faint signals that axions might produce. Like the WIMP searches, axion experiments have so far come up empty, though they've only scratched the surface of the possible parameter space where axions might exist. Some physicists have even proposed that dark matter might not be particles at all, but primordial black holes that formed in the very early universe, perhaps during the first fraction of a second after the Big Bang. These wouldn't be the black holes we normally think about, formed from collapsing stars. Instead, they'd be much smaller and much older, scattered throughout space, collectively providing the gravitational effects we attribute to dark matter. It's a creative idea, and one that the famous physicist Stephen Hawking explored, but observations have ruled out primordial black holes as the primary explanation for dark matter. They could make up a small fraction of the dark matter, perhaps, but they can't account for all of it. The truth is, we might be looking at the problem all wrong. Some theorists have suggested that maybe we don't need dark matter at all. Maybe instead, the laws of gravity themselves need to be modified on very large scales. These modified theories of gravity, with names like MOND for modified Newtonian dynamics, attempt to explain galactic rotation curves and other observations without invoking dark matter. They've had some success in explaining certain phenomena, but they struggle with others, particularly the detailed patterns in the cosmic microwave background and the behavior of colliding galaxy clusters. Most physicists think the evidence overwhelmingly points toward dark matter being real, whatever it is, rather than gravity needing modification. But the possibility remains open, a reminder that we might be missing something fundamental about how the universe works. As you lie there, relaxing, consider this thought. Right now, at this very moment, countless dark matter particles are passing through your body. If dark matter particles exist in the form most theories predict, billions of them are streaming through you every second, passing through the earth, through the walls of your room, through your very atoms, without leaving a trace. They don't collide with anything, don't interact with the matter that makes up your body or the world around you, except through the faintest whisper of gravitational attraction. You are completely transparent to them, as they are to you. All around us, perhaps making up 5/6 of all the matter in the universe, is this vast, invisible ocean of dark matter, and we move through it like ghosts, never touching it, never sensing it directly, knowing it's there only because of how it shapes the cosmos on the largest scales. It's a humbling reminder of how much we still don't understand about the universe we inhabit. The scaffolding that holds all of reality together, the gravitational glue that prevents galaxies from flying apart and makes the large-scale structure of the cosmos possible, is made of something we can't see, can't detect directly, and don't comprehend. Magnetars, the universe's strongest magnets. Now, let's turn our attention to something we can actually observe. Objects so extreme that they challenge our understanding of what matter and magnetic fields can do. We're talking about magnetars, the undisputed champions when it comes to magnetic field strength, objects so magnetic that they make the Earth's magnetic field, which protects us from solar radiation and makes compasses work, look like a barely noticeable whisper by comparison. To understand magnetars, we first need to understand their parent objects, neutron stars, which are themselves among the most extreme things in the universe. Neutron stars form when massive stars, typically between 8 and 20 times the mass of the Sun, reach the end of their lives. A star like our Sun shines by fusing hydrogen into helium in its core, a process that creates tremendous outward pressure that balances the inward pull of gravity. When a star runs out of hydrogen, it begins fusing helium into heavier elements like carbon and oxygen. More massive stars continue this process, fusing progressively heavier elements up the periodic table: silicon, sulfur, iron. But iron is where this process comes to a screeching halt. Fusing iron doesn't release energy, it actually requires energy. So, when a massive star's core becomes primarily iron, it suddenly loses the pressure that was supporting it against gravity. What happens next is one of the most violent events in the universe. The core collapses catastrophically, falling inward in a fraction of a second. In that collapse, the core's density becomes so extreme that protons and electrons are literally crushed together, combining to form neutrons. The collapse continues until the neutrons themselves resist further compression through a quantum mechanical effect called degeneracy pressure. the same principle that prevents electrons from occupying the same quantum state. The collapse stops when the neutrons are packed as tightly as quantum mechanics allows, creating an object roughly 12 to 15 miles across but containing 1.5 to 2 times the mass of the Sun. That's roughly 500,000 times the mass of the entire Earth compressed into a sphere about the size of Manhattan. To truly grasp this density, imagine taking Mount Everest, all 10 trillion tons of it, and compressing it down until it fits in a thimble. That's approximately the density of a neutron star. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. If you could somehow take a cubic centimeter of neutron star material, smaller than a sugar cube, it would weigh as much as all of humanity combined. These objects are so dense that they warp spacetime significantly around themselves. Light passing near a neutron star bends noticeably, and time flows measurably slower on the surface than it does far away in normal space. If you were standing on a neutron star, which would be instantly fatal for many reasons, you'd weigh about 1 billion times more than you do on Earth. The gravity is so intense that the escape velocity, the speed you'd need to break free of the neutron star's gravitational pull, is about 1/3 the speed of light. Neutron stars also spin, and they spin fast. When a star collapses, conservation of angular momentum causes it to spin up, like a figure skater pulling in her arms during a spin. Some neutron stars rotate hundreds of times per second, completing a full rotation in just a few milliseconds. These rapidly spinning neutron stars often become pulsars, objects that emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space like a lighthouse beacon, and if Earth happens to lie in the path of the beam, we detect regular pulses of radio waves or other radiation with incredible precision. The fastest known pulsar, discovered in 2006, spins 716 times every second. That means its equator is moving at about 1/4 of the speed of light. These objects are cosmic timepieces, their pulses so regular that they rival atomic clocks in their precision. But neutron stars also have magnetic fields, and those fields are truly remarkable. Even a typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. That's already difficult to comprehend. Earth's magnetic field is strong enough to deflect charged particles from the Sun, creating the auroras we see near the poles. A neutron star's magnetic field would completely dominate any magnetic field we could create in a laboratory. But magnetars take this to an entirely new level. Magnetars have magnetic fields that are about 1,000 times stronger than those of regular neutron stars, reaching strengths of around 100 trillion to 1 quadrillion Gauss. That's roughly 1,000 trillion times stronger than the Earth's magnetic field, and 1 billion times stronger than the strongest magnetic field we've ever created in a laboratory. To put this in perspective, if you were to somehow survive and float 600 miles away from a magnetar, well outside the Kármán line that marks the edge of Earth's atmosphere, the magnetic field would be strong enough to distort the electron orbitals in the atoms of your body. The atoms themselves would change shape, becoming elongated in the direction of the magnetic field. Hydrogen atoms, normally spherical, would be squeezed into cigar-like shapes, becoming about 200 times narrower in one direction. Your biochemistry, which depends on the specific shapes and interactions of molecules, would simply stop working. You wouldn't even need to get close to die from a magnetar's magnetic field. If a magnetar somehow appeared at the distance of the moon, about 240,000 miles away, it would wipe the magnetic strips on every credit card on Earth. Every hard drive would be erased. Electronic devices would fail. The Magnetars field would overwhelm Earth's own magnetic field completely. The magnetar itself struggles against its own magnetic field. The field is so strong that it exerts tremendous stress on the neutron star's crust, which is thought to be made of a crystalline lattice of iron nuclei. Imagine the crust of the neutron star as being locked together with its magnetic field, so that changes in one affect the other. The magnetic field slowly decays over time, but as it does, it creates shifting stresses in the crust. Eventually, these stresses become too great, and the crust cracks in what's called a starquake. When this happens, the magnetic field suddenly reconfigures itself, and enormous amounts of energy are released in a violent explosion. In a fraction of a second, a magnetar can release more energy than our sun emits in 100,000 years. This energy comes out primarily as gamma rays and X-rays, the highest energy forms of electromagnetic radiation, and it erupts from the magnetar in a burst that can be detected from thousands or even millions of light years away. One of the most famous magnetar flares occurred on March 5, 1979, when two Soviet spacecraft, Venera 11 and 12, which were monitoring Venus, were suddenly hit by a blast of gamma radiation. Their radiation detectors went from measuring about 100 counts per second to over 200,000 counts per second in just a millisecond. The burst was so intense that it actually ionized atoms in Earth's upper atmosphere, causing the ionosphere to suddenly change its properties. Later analysis showed that this burst came from a magnetar called SGR 052666 in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way located about 160,000 light-years away. Think about that for a moment. An object the size of a city, located 160,000 light-years away, released so much energy in a fraction of a second that it had measurable effects on Earth's atmosphere. If that same magnetar had been just 10 light-years away, close enough to be one of our nearest stellar neighbors, its burst would have stripped away much of Earth's ozone layer, potentially causing a mass extinction. The mechanism that produces magnetars is still being studied, but the leading theory involves the birth conditions of the neutron star. When a massive star collapses, the conditions have to be just right. The star needs to have been rotating rapidly, and there needs to be vigorous convection and turbulent motion in the collapsing material. Under these conditions, a dynamo mechanism can amplify the magnetic field to extraordinary levels. It's similar to how Earth's magnetic field is generated by the motion of molten iron in its core, but on steroids. The extreme density, rapid rotation, and turbulent conditions during the neutron star's formation create a magnetic field that is boosted to magnetar levels. It's estimated that about 1 in 10 supernova explosions produces a magnetar rather than a regular neutron star, which means magnetars, while rare, are not impossibly uncommon. As of 2021, about 30 confirmed magnetars are known in our galaxy, but given how difficult they are to detect and how short-lived their active phase is, there are probably many more. Some estimates suggest there could be 30 million or more inactive magnetars in the Milky Way. Dead magnetars whose magnetic fields have decayed below the level where they produce observable emissions. Magnetars have recently become even more interesting because they might explain one of the great cosmic mysteries we'll discuss shortly, fast radio bursts. In 2020, astronomers detected a fast radio burst coming from a known magnetar in our own galaxy, SGR 1935 Plaza 2154. This was the first time anyone had managed to pinpoint the source of a fast radio burst, and the fact that it came from a magnetar suggests that at least some of these mysterious bursts might be caused by these ultramagnetic neutron stars. The connection makes sense. Magnetars have the extreme magnetic fields and energetic processes necessary to generate the incredible bursts of radio waves that we observe. When their magnetic fields reconfigure during a starquake, the resulting explosion might accelerate particles to nearly the speed of light, creating conditions perfect for producing intense radio emission. As you relax and let this information settle in your mind, consider that magnetars represent matter pushed to one of its fundamental limits. They're not quite as extreme as black holes, where matter collapses beyond any hope of recovery, but they're close. They represent a kind of boundary where normal matter, even in its most compressed form, can just barely exist before crossing over into something else entirely. The atoms that make up your body, the air you breathe, the ground beneath you, all of this matter exists in a relatively gentle, hospitable state. But compress that matter, spin it, heat it, magnetize it to extreme levels, and you get something that barely resembles matter as we know it anymore. You get a cosmic object so strange that it challenges our definitions, so extreme that our everyday experience provides no context for understanding it. And yet these objects exist out there, scattered through our galaxy, spinning silently in the darkness, occasionally flaring to life in bursts of energy that outshine their neighbors by factors of billions or trillions. They're real, they're measurable, they're observable, and they're absolutely, profoundly strange. White holes, time's reverse door. Now, let's venture into territory that's even more speculative, more theoretical, more at the edge of what physics allows. We're going to talk about white holes, objects that might not exist at all, but if they did, would represent one of the most profound challenges to our understanding of time, causality, and the fundamental nature of reality. White holes are, in a sense, the perfect mirror image of black holes, and understanding them requires us to think about time in ways that might feel deeply unnatural. Black holes are regions of space-time where the gravitational pull becomes so intense that nothing, once it crosses the event horizon, can ever escape. Everything that passes that boundary is doomed to fall inward toward the singularity at the center, where density becomes infinite and our laws of physics break down. We understand black holes reasonably well because we've observed them, detected their gravitational waves when they merge, and even captured images of their event horizons. But Einstein's equations of general relativity, the mathematical framework that predicted black holes in the first place, have an interesting property. They're time-symmetric. That means if you have a solution to Einstein's equations, you can run it backward in time and get another valid solution. If you take the mathematics describing a black hole and reverse the direction of time, you get a white hole. A white hole would be a region of space-time where nothing can enter from the outside, but matter and energy can escape from it. It's like a boundary of ultimate rejection, space's most exclusive club where absolutely nothing is allowed in. While a black hole has an event horizon that acts as a one-way membrane allowing things to enter but never leave, a white hole would have an event horizon that only permits things to leave, never to enter. From the perspective of someone outside, a white hole would appear to be violently ejecting matter and energy. You might imagine it as a cosmic fountain, continuously spewing material outward into the universe while refusing to accept anything trying to fall in. The mathematics works perfectly. The equations allow for white holes just as cleanly as they allow for black holes. In fact, in the most general solution to Einstein's equations for a black hole, something called the maximally extended Schwarzschild solution, white holes naturally appear. They're part of the complete picture of what a black hole's spacetime looks like. But there's a massive problem with white holes, several problems actually, that make most physicists deeply skeptical that they could exist in our universe. The first problem is formation. We know how black holes form through a well-understood physical process. A massive star exhausts its nuclear fuel, its core collapses catastrophically, and if the core is massive enough, nothing can stop the collapse. It continues until it forms a black hole. This is a natural, physical process that we can observe happening in the universe. But white holes? There's no known process that would create them. A white hole would need to have existed from the very beginning of the universe, built into the initial conditions of the Big Bang itself, or they'd need to form through some exotic quantum process we don't understand. Neither option is very satisfying. Why would the Big Bang create white holes? What purpose would they serve? And if they formed later, through what mechanism? The second problem is stability. Even if a white hole somehow formed, it probably wouldn't last very long. Imagine a white hole sitting in space, continuously ejecting matter and energy. That material has to go somewhere, and some of it would likely end up in orbit around the white hole or floating nearby. But here's the issue. While nothing can fall into a white hole according to the pure mathematics, in reality, the white hole would be unstable. Any tiny disturbance, any small amount of matter that got close enough would likely cause the white hole to collapse and convert into a black hole. It's similar to how a pencil balanced perfectly on its point would technically be in equilibrium, according to simple physics. But in reality, the slightest breeze or vibration would cause it to fall. White holes, if they existed, would be in an unstable equilibrium, teetering on the edge of collapsing into black holes. The third problem is thermodynamics. Our universe has a fundamental asymmetry when it comes to time. Entropy, the measure of disorder in a system, always increases over time. This is the second law of thermodynamics, one of the most fundamental principles in all of physics. It's what gives time its arrow, its direction. A white hole, which operates like a black hole running backward in time, would violate this principle. It would be an object that decreases entropy, creating order from disorder, running counter to the fundamental direction that time flows in our universe. Some physicists argue that this violation of thermodynamics is enough by itself to rule out the existence of white holes in our cosmos. The universe simply doesn't run that way. But despite all these problems, white holes remain fascinating to theoretical physicists because they connect to some of the deepest questions about black holes and quantum mechanics. One of the great mysteries of black holes is what happens to information that falls into them. According to classical general relativity, information that crosses the event horizon is lost forever, trapped behind the boundary, and eventually crushed in the singularity. But quantum mechanics says that information can never be truly destroyed. This tension is called the black hole information paradox, and it's been one of the central puzzles in theoretical physics for decades. White holes offer a potential resolution to this paradox. What if black holes don't last forever? What if, through quantum mechanical effects, so Black hole eventually transforms into a white hole. In this scenario, all the matter and information that fell into the black hole over its lifetime would eventually be ejected back out through the white hole phase. The information isn't destroyed. It is simply stored for an unimaginably long time before being rebroadcasted into the universe. Section 5. Fast radio bursts, cosmic lightning discovery and properties. The universe is a vast, silent ocean, but every so often it is pierced by a flash of light so intense and so brief that it challenges our fundamental understanding of high-energy physics. These are fast radio bursts, or FRBs. For decades, radio telescopes scanned the heavens, collecting data that mostly consisted of the steady hum of pulsars or the static of the cosmic microwave background. However, in 2007, a team led by Duncan Lorimer discovered something hidden in archival data from the Parkes Observatory in Australia. They found a burst of radio waves that lasted only 5 milliseconds. Despite its brevity, the energy contained in that single pulse was equivalent to the total output of the Sun over the course of 80 years. This first discovery, now famously known as the Lorimer burst, opened a new chapter in astronomy. But what exactly defines an FRB? Their most defining characteristic is their dispersion measure, DM. As light travels through the ionized gas of the intergalactic medium, lower frequencies are slowed down more than higher frequencies. By measuring the delay between the arrival of high-frequency and low-frequency radio waves, astronomers can calculate how much matter the signal passed through. For FRBs, the dispersion is enormous, far greater than anything that could be caused by the gas within our own Milky Way. This was the definitive proof that these signals are extragalactic, originating billions of light-years away. They are not local glitches. They are messengers from the deep past of the cosmos. The mystery of their origin. The sheer power and short duration of FRBs present a massive theoretical hurdle. To produce such a concentrated burst of energy, the source must be incredibly small, likely no larger than a few hundred kilometers across. In the world of astrophysics, small and powerful usually points to compact objects, white dwarfs, neutron, stars, or black holes. Initially, the prevailing theory was that FRBs were the result of cataclysmic events, the kind of things that only happen once because the source is destroyed in the process. Examples include two neutron stars colliding to form a black hole, or a massive star collapsing in a supernova. However, as we began to detect more of these bursts, the one-off theory started to crumble. If the source is destroyed, how could we ever see a second burst from the same location? This led to the realization that the engine behind these bursts must be something capable of surviving the event. The mystery deepened when we realized that most FRBs are detected in galaxies with high rates of star formation, suggesting a link to the life cycles of massive stars. Yet, some have been found in old, dead elliptical galaxies where star formation ceased billions of years ago. This suggests that there might be multiple ways to create an FRB, or that our single leading theory must be flexible enough to inhabit very different environments. Repeating versus non-repeating FRBs. The discovery of FRB 121102 was a watershed moment. Unlike the Lorimer burst, which was never heard from again, FRB 121102 began to repeat. Over the years, it has fired off hundreds of bursts. This discovery split the field into two camps, the repeaters and the non-repeaters. Repeating FRBs are a goldmine for scientists. Because they fire multiple times, we can point multiple telescopes, including optical, X-ray, and gamma-ray observatories, at the exact same spot in the sky to see what lies there. This allowed us to pinpoint FRB 12.1 to a tiny dwarf galaxy 3 billion light-years away. Interestingly, the repeating bursts don't always happen at random. Some sources show a periodic cycle. For instance, FRB 180916 JZ 158 plus in 65 has a 16-day cycle where it bursts for 4 days and then goes silent for 12. This periodicity suggests a clock-like mechanism, perhaps a star orbiting a black hole or a wobbling, highly magnetized neutron star. Non-repeaters remain more mysterious. Are they truly one-time events, like the collision of two dense stars, or are they just repeaters that haven't repeated yet? If we wait 1,000 years, will every FRB eventually fire again? Some statistical models suggest that the energy distribution of non-repeaters is different, implying they might indeed be caused by the final, violent deaths of cosmic objects, whereas repeaters are produced by long-lived, stable engines. Possible explanations, including magnetars. The most promising engine for an FRB is the magnetar. A magnetar is a type of neutron star, the collapsed core of a massive star, but with a twist. It possesses the most powerful magnetic fields in the known universe, roughly 1,000 trillion times stronger than Earth's. These fields are so intense that they exert a physical pressure on the star's crust. Occasionally, the crust snaps under the stress, a starquake. This event releases a titanic amount of energy in the form of gamma rays and radio waves. In April 2020, the mystery moved from theoretical to observed. 2 radio telescopes, KIME in Canada and STARE-2 in the U.S., detected a massive radio burst coming from a magnetar within our own galaxy, SGR 1935-2154. This was a galactic FRB. While it was slightly less energetic than the ones we see from billions of light-years away, it proved that magnetars are capable of producing the exact type of millisecond duration radio pulse we identify as an FRB. But even with magnetars as the lead suspect, puzzles remain. Some FRBs are so powerful that even a magnetar's starquake seems insufficient to explain them. This has led to more exotic theories. Could they be caused by superradiance, where a plasma cloud amplifies light like a cosmic laser? Or perhaps they are produced by cosmic combs, where the solar wind from a nearby star interacts with a magnetar's magnetosphere. There is even the technosignature hypothesis, suggested by some Harvard physicists, that these could be the leakage from massive planetary-sized transmitters used by advanced civilizations to power light sails for interstellar travel. While the magnetar theory is currently the strongest, the variety in FRB behavior, some repeating, some periodic, some extremely powerful, some localized in young galaxies, and others in old, suggests that we may be looking at a family of phenomena rather than a single type of event. As our telescopes become more sensitive, we are now detecting dozens of FRBs every day. We are moving from the era of discovery to the era of population studies, where we can use these bursts as tools to map the missing matter of the universe. Because these radio waves interact with the gas between galaxies, they carry a record of everything they passed through. They are not just mysteries to be solved, they are the flashlights that illuminate the dark, invisible structures of the cosmic web. Section 6. Cosmic Strings. Cracks in reality formation in the early universe. To grasp the concept of cosmic strings, we must look back to the most violent and transformative era of the universe, the first microsecond after the Big Bang. During this epoch, The universe was a superheated soup of energy, and the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were likely unified into a single, perfect force. As the universe expanded and cooled, it underwent a series of phase transitions, much like steam condensing into water or water freezing into ice. In physics, when a material undergoes a phase transition, it rarely does so perfectly. Consider a lake freezing over. The ice doesn't form as one single, flawless crystal. Instead, ice crystals begin to form in different spots and grow until they meet. Where these disparate regions of ice collide, they create cracks, bubbles, and opaque lines. These are known as topological defects. According to grand unified theories, guts, the vacuum of space itself underwent similar transitions. As the Higgs-like fields that govern the fundamental forces settled into their new states, they didn't always align perfectly across the vast distances of the expanding cosmos. The cracks formed by these misalignments are what we call cosmic strings. These are not just lines in space, they are trapped remnants of the high-energy state of the early universe, preserved as one-dimensional threads of primordial vacuum. Properties and characteristics. A cosmic string is perhaps the most paradoxical object ever conceived in theoretical physics. It is a one-dimensional object, meaning it has length but effectively zero thickness, theoretically thinner than a proton, roughly 10^30 centimeters. However, despite having no width, it is unimaginably massive. The tension and energy density of a string are determined by the energy scale of the phase transition that created it. For a string formed at the grand unification scale, a single centimeter of that string would weigh about 10 adars, $12 tons. If you had a piece of cosmic string only as long as a football field, it would weigh as much as the entire Earth. Because they are under such immense tension, cosmic strings act like giant relativistic rubber bands. They do not sit still. They whip through the vacuum of space at speeds approaching the speed of light. They are also incredibly long, either forming closed loops that vibrate or stretching in infinite lines across the entire observable horizon. When these strings interact, they exhibit a behavior called reconnection. If two strings cross, they don't simply pass through each other. They snap and swap ends, often flinging off smaller vibrating loops in the process. These loops are the death cries of the string network, as they vibrate so intensely that they eventually radiate all their energy away as gravitational waves and vanish into nothingness. Incredible density and effects on spacetime. The gravity of a cosmic string is unlike the gravity of a planet or a star. A spherical object like the Sun curves spacetime into a bowl, causing objects to fall toward its center. A cosmic string, however, curves spacetime into a cone. If you were to travel in a complete circle around a cosmic string, you would find that you have traveled less than 360 degrees. This angle deficit creates a unique geometry. Imagine a circle of paper with a small wedge cut out of it. When you tape the remaining edges together, you get a cone. This conical geometry has a startling effect on light. If a cosmic string lies between us and a distant galaxy, the light from that galaxy can travel around both sides of the string's wedge. Because spacetime is missing in the middle, both paths are straight lines, but they arrive at our telescopes from slightly different directions. This results in gravitational lensing, but with a specific signature. We would see two identical, undistorted images of the same galaxy. Unlike the Einstein rings, or smeared arcs caused by the gravity of massive galaxy clusters, cosmic string lensing would produce perfect twins, separated by a tiny fraction of a degree. Furthermore, because these strings are so dense and move so fast, they create wakes behind them. As a string sweeps through the interstellar medium, its conical gravity causes matter to rush toward the plane behind the string. In the early universe, these wakes could have acted as gravitational nets, trapping gas and dark matter, and potentially jump-starting the formation of the first large-scale structures, like galaxy filaments. Why we haven't found them yet. Despite being a staple of theoretical cosmology since the 1970s, we have yet to confirm the existence of a cosmic string. The primary reason is their sheer fineness. Even though they are massive, their subatomic width makes them impossible to see directly with light. We are hunting for ghosts that only reveal themselves through their gravitational influence. Scientists have spent decades looking for the double image signature in deep space surveys. While we have found several candidate pairs, most notably the CSO-1 pair, further investigation usually reveals that they are just two different galaxies that happen to look alike, or a single galaxy lensed by a more conventional black hole. Another search method involves the cosmic microwave background, CMB, the afterglow of the Big Bang. A moving string would leave a scar in this radiation, a temperature shift known as the Kaiser-Stebbins effect. However, data from the Planck satellite has shown no such scars, which tells us that if strings exist, their tension, Gmo, must be much lower than the simplest gut models predicted, less than 1 part in 10 million. The most promising current search is through gravitational wave background detection. If the universe is filled with a network of these strings, the constant snapping and vibrating of loops should create a stochastic hum of gravitational waves. Recently, pulsar timing arrays like nanograv have detected a low-frequency gravitational wave background. While many believe this comes from merging supermassive black holes, some of the data fits the string model remarkably well. We may already be hearing them. We just haven't learned to distinguish their voice from the crowd yet. Connection to string theory. It is a common point of confusion, but cosmic strings and the strings in string theory are technically different concepts, though they might be related. In traditional cosmology, cosmic strings are topological defects, cracks. In string theory, fundamental strings are the tiny, vibrating building blocks of all particles. However, modern string theory, specifically brane inflation models, suggests that these fundamental strings could have been stretched to astronomical sizes during the rapid expansion of the universe. These supercosmic strings would be even more exotic than the topological variety. They could come in different types, F strings and D strings, and could have junctions where multiple strings meet like a spiderweb. If we were to detect a cosmic string and find that it has these specific properties, it wouldn't just be a discovery in astronomy. It would be the first direct, experimental proof of string theory. It would mean that the fundamental DNA of the universe has been magnified to a scale where we can actually measure it, bridging the gap between the infinitely small and the infinitely large. In essence, cosmic strings are the fossils of the Big Bang. To find one would be to touch the moment of creation, providing us with a direct link to the high-energy physics of the beginning of time. They are the ultimate large-scale oddity, representing the moment the universe's perfect symmetry shattered into the reality we inhabit today. Section 7. The Fermi Bubbles. Our Galaxy's Mystery Discovery and Structure. In the year 2010, astronomers using the Fermi Gamma Ray Space Telescope announced a discovery that fundamentally changed our map of the Milky Way. Hidden in plain sight, masked by the glare of the galaxy's disk, were two colossal structures of high-energy radiation. These Fermi bubbles are gargantuan lobes of gamma-ray emission that extend 25,000 light-years above and below the galactic plane. To put that into perspective, the bubbles are roughly as tall as the Milky Way's radius. If they were visible to the naked eye, they would span more than half of the night sky, towering over the constellations we know. The structure of these bubbles is strikingly symmetrical and well-defined. They are not amorphous clouds of gas, but appear to have sharp, distinct edges. They emerge from the very center of our galaxy, near the constellation Sagittarius, and expand outward into the galactic halo. While they were first identified in gamma rays, the most energetic form of light, subsequent observations by the XMM, Newton, and Suzaku satellites revealed that they also emit X-rays. More recently, radio telescopes have detected polarized radio emissions that trace the edges of these lobes. The skin of the bubbles is composed of extremely hot, ionized gas, while the interior is filled with cosmic rays and magnetic fields that accelerate particles to nearly the speed of light. Theories about their origin. The discovery of the Fermi bubbles immediately sparked a heated debate. What could possibly have the power to blow such massive structures out of the center of a galaxy? There are two primary competing theories, both of which suggest that the Milky Way was much more violent in the recent past than it is today. The first theory is the starfall, or starburst, hypothesis. This suggests that several million years ago, the galactic center experienced a sudden and massive surge in star formation. Thousands of giant stars would have been born, lived fast, and died in a rapid-fire sequence of supernova explosions. The combined energy of these thousands of supernovae would have created a galactic wind, powerful enough to push the surrounding gas out into the halo, creating the bubbles we see today. However, critics point out that the bubbles are remarkably symmetrical and have very sharp edges, which is difficult to achieve with a chaotic series of individual explosions. The second, and currently more favored theory, is the black hole jet hypothesis. This theory points the finger at Sagittarius A, the supermassive black hole at the heart of our galaxy. While Sagittarius A-Aus is relatively quiet now, it may have undergone an active phase between 2 and 6 million years ago. If a large cloud of gas or even a star wandered too close and was devoured, the black hole would have produced immense jets of plasma, shooting out from its poles at relativistic speeds. These jets would have acted like a pair of cosmic blowtorches, inflating the bubbles of hot gas in the galactic halo. This model better explains the symmetry and the sheer scale of the structures, as black hole jets are known for their precision and power. Connection to Sagittarius A. The link between the Fermi bubbles and Sagittarius AE is more than just geographical. It provides a smoking gun for the history of our galaxy's central engine. For a long time, the Milky Way was considered a quiet galaxy compared to active galactic nuclei, AGN, or quasars found in the distant universe. The Fermi bubbles prove that our black hole isn't just a dormant weight. It has a history of dramatic outbursts. Recent data from the Hubble Space Telescope has added a new layer to this connection. By looking at the light from distant quasars as it passes through the bubbles, astronomers have measured the speed of the gas within the lobes. The gas is moving at a staggering 2 million miles per hour. By calculating backward, scientists have estimated that the event that created the bubbles occurred roughly 3.5 million years ago. a mere blink of an eye in cosmic time. At that time, our early human ancestors, like Australopithecus, were already walking the Earth. If they had been able to see in the gamma-ray spectrum, they would have seen a massive, glowing explosion at the center of the sky, perhaps as bright as the moon. Ongoing mysteries. Despite over a decade of study, the Fermi bubbles continue to surprise us with new oddities. In 2012, a new feature was discovered within the bubbles, the gamma-ray jets. These are thinner, even more energetic streaks of radiation that seem to be nested inside the larger lobes. If the bubbles are the exhaust from an engine, the jets are the direct blast. However, not all telescopes see these jets, leading to a debate over whether they are real or just an artifact of how we process the data. Another mystery is the discovery of the Rosetta bubbles. In 2020, the ESA Rosetta X-ray telescope found even larger bubbles, extending 45,000 light-years, that encompass the Fermi bubbles like an outer shell. This suggests that the galactic center has had multiple outbursts over millions of years. Are these bubbles a recurring feature? Does the Milky Way breathe, expanding these lobes every few million years when the black hole gets fed? Furthermore, there is the question of the dark matter signal. Some researchers have argued that the center of the Fermi bubbles contains an excess of gamma rays that cannot be explained by pulsars or black hole activity alone. Some suggest this could be evidence of dark matter particles annihilating each other in the dense galactic core. While this remains a controversial fringe theory, it highlights how the Fermi bubbles serve as a laboratory for the most fundamental questions in physics. The Fermi bubbles remind us that we live in a dynamic, changing system. Our galaxy may look like a static spiral of stars, but beneath that calm exterior lies a history of cataclysmic events. The bubbles are the fading echoes of a time when the heart of the Milky Way roared with the power of 1,000 suns, and they stand as a monument to the invisible forces that shape our cosmic home. Section 8. The Cosmic Web and Large-Scale Oddities Structure of the Universe. When we look at the night sky, we see stars and galaxies scattered across the darkness, appearing almost like random points of light. However, when we zoom out to the furthest possible scales, spanning billions of light-years, a hidden architecture emerges. The universe is not a chaotic soup. It is organized into a gargantuan, interconnected network known as the cosmic web. This is the largest coherent structure in existence, a skeletal framework that defines where matter can and cannot exist. The cosmic web is composed of three primary components: dense nodes, long filaments, and vast, empty voids. The nodes are the cities of the universe, massive clusters of galaxies held together by immense gravitational forces. Connecting these nodes are the filaments, long highways of gas and dark matter that stretch across hundreds of millions of light-years. It is along these filaments that galaxies form and migrate, drawn by gravity toward the dense clusters. Finally, there are the voids, monstrously large deserts of nothingness that can be 300 million light-years across, containing almost no galaxies at all. This structure was born from the tiniest fluctuations in the early universe. In the moments after the Big Bang, some regions of space were slightly denser than others. Over billions of years, gravity acted as an amplifier, pulling more matter into the dense regions and emptying out the less dense ones. What we see today is the result of that 13.8 billion-year tug-of-war. The cosmic web is essentially the map of gravity's victory over the expansion of the universe. odd radio circles, ORCs. As we have mapped this web, we have encountered anomalies that defy standard classification. One of the most recent and baffling discoveries is the odd radio circle, or ORC. First detected in 2019 by the Australian Square Kilometre Array Pathfinder, ESCAPE. These are perfect, ring-like structures of radio emission. They are ghosts in the machine. They are invisible to optical, X-ray, and infrared telescopes. Only in the radio spectrum do these giant, glowing hoops appear. What makes ORCs so strange is their size and symmetry. Each circle is roughly 1 million light-years across, 10 times larger than the Milky Way. At their center, there is usually a distant galaxy, which suggests the galaxy is the source of the circle. However, the origin of the hoop itself is a mystery. Is it a spherical shock wave from a massive explosion at the center of the galaxy? Is it the result of two supermassive black holes merging? Or is it a throat of a wormhole seen from the end? While recent studies suggest they might be shells of gas blown out by intense starburst activity, the sheer perfection of their circular shape remains an oddity that doesn't quite fit our existing models of galactic outflows. Dark flow. While the cosmic web provides the structure, the movement of matter, within that structure provides the next great mystery, dark flow. According to the standard model of cosmology, the expansion of the universe should be uniform in all directions. While galaxies move toward each other due to local gravity, like the Milky Way moving toward Andromeda, on a large enough scale, everything should be moving apart at a predictable rate. However, in 2008, astronomers discovered a controversial trend. Large clusters of galaxies appeared to be drifting in a specific direction, toward a patch of sky between the constellations of Centaurus and Vela, at speeds of nearly 2 million miles per hour. This motion wasn't caused by the expansion of the universe, nor could it be explained by the gravity of any visible matter within our observable horizon. This led to the dark flow hypothesis, the idea that something outside our observable universe is pulling on us. If the universe underwent a period of rapid inflation, there might be massive structures, other universes, or gargantuan concentrations of matter, lying far beyond the 46 billion light-year limit of what we can see. Their gravitational reach could be tugging on the matter within our horizon, creating a cosmic current that we are only just beginning to detect. While the existence of dark flow is still debated among cosmologists, it hints that our observable bubble might be just a small, influenced part of a much larger, weirder reality. The universe's organization. The more we study the organization of the universe, the more we realize that it behaves like a complex biological system. Some physicists have even noted the striking resemblance between the cosmic web and the neural network of a human brain. While this is likely a coincidence of mathematical laws, specifically how networks optimize connections, it raises deep questions about the fine-tuning of the cosmos. The organization of the universe is governed by a delicate balance between dark matter and dark energy. Dark matter acts as the glue, providing the gravitational scaffolding for the web. Dark energy acts as the expander, pushing the voids apart and stretching the filaments. The destiny of the cosmic web depends on which of these two forces wins. Current observations suggest that dark energy is accelerating, meaning that in the far future, the filaments will eventually snap, the nodes will drift apart, and the beautiful, interconnected web will dissolve into an island universe of isolated clusters, separated by an infinite, unreachable darkness. Understanding the cosmic web is not just about mapping galaxies, it's about understanding the limits of our knowledge. When we see structures like the Hercules Corona Borealis Great Wall, a filament so large it accounts for 10% of the diameter of the observable universe, we are forced to ask if our current theories can even account for such size. The large-scale oddities of our universe suggest that the map is much bigger than we previously imagined, and we are only beginning to find the landmarks. Section 9. Quantum Phenomena in Space Plasma and Its Strange Behavior. When we think of matter in space, we often imagine cold rocks or burning balls of gas. However, 99% of the observable universe exists in a fourth state of matter, plasma. Plasma is created when gas is heated to such extreme temperatures or subjected to such intense radiation that electrons are stripped from their atoms. This creates a soup of free-moving charged particles, ions, and electrons. Because these particles carry electrical charges, plasma does not behave like the air on Earth. It is governed by the laws of electromagnetism as much as by gravity, leading to behaviors that seem to defy the standard rules of fluid dynamics. In the vacuum of space, plasma acts as a conductor of immense cosmic currents. It can form long, glowing filaments or Birkeland currents that channel energy across light years. Because plasma is magnetically frozen, a concept where the magnetic field lines move along with the fluid, it can store vast amounts of elastic energy, much like a stretched rubber band. When these fields become too twisted or compressed, they snap, leading to some of the most violent events in the universe. This strange collective behavior of plasma is what powers the solar wind, creates the beautiful auroras on Earth, and serves as the medium through which quantum effects can manifest on a macroscopic, astronomical scale. Magnetic reconnection. One of the most critical and mysterious processes in space plasma is magnetic reconnection. In the simple physics we learn in school, magnetic field lines are described as continuous loops that never cross. However, in the high-energy environment of space, such as the boundary between the Earth's magnetosphere and the Sun's solar wind, these field lines can break and reconnect in a new configuration. When this happens, the magnetic energy stored in the plasma is instantaneously converted into kinetic energy and heat. This process acts like a cosmic slingshot, accelerating particles to nearly the speed of light in a fraction of a second. Magnetic reconnection is the engine behind solar flares, which can release the energy of millions of hydrogen bombs. On a larger scale, it occurs in the accretion disks of black holes and the magnetospheres of pulsars. Despite its importance, we still don't fully understand the trigger that causes the field lines to snap. It is a bridge between the macroscopic world of magnetic fields and the microscopic world of particle physics, where quantum fluctuations may play a role in initiating the break. Frame dragging. Moving from the electromagnetic to the gravitational, we encounter one of the most mind-bending predictions of Einstein's general relativity. Frame dragging, also known as the lens-Thirring effect. While we usually think of gravity as a pull, Einstein realized that space and time are a fabric. If a massive object like a star or a black hole rotates, it doesn't just sit in that fabric. It drags the fabric of space-time around with it, like a spoon spinning in a jar of thick honey. This isn't just a theoretical curiosity. It has been measured. Around a rapidly spinning black hole, frame dragging is so intense that there is a region called the ergosphere. In this region, it is physically impossible to stand still, no matter how powerful your engines are. Space-time itself is moving faster than the speed of light relative to an outside observer. This effect allows for a theoretical process called the Penrose process, where an object could enter the ergosphere, split in two, and have one half escape with more energy than it started with, essentially stealing energy from the black hole's rotation. This quantum-scale interaction with the geometry of the universe shows that space is not a void, but a physical substance that can be twisted and churned. Exotic states of matter in extreme conditions, space provides a laboratory for states of matter that are impossible to recreate or sustain on Earth. In the hearts of neutron stars, the pressure is so great that atoms themselves collapse. Electrons are forced into protons, creating a star made almost entirely of neutrons. But even deeper, at the core, we may find quark-gluon plasma. This is a perfect fluid where even neutrons dissolve, leaving a sea of up, down, and strange quarks floating freely. This state of matter hasn't existed naturally since the first microseconds of the Big Bang. Another exotic phenomenon is the potential for superfluidity and superconductivity inside neutron stars. On Earth, these states require temperatures near absolute zero. In space, however, the extreme density allows the interior of a star at millions of degrees to behave like a zero-friction fluid. This can lead to glitches, sudden increases in a pulsar's rotation speed, as the superfluid interior slips against the solid crust. Finally, we have the theoretical time crystals and Bose-Einstein condensates that may form in the cold, dark corners of the cosmic web. These are states where quantum effects, usually limited to the scale of an atom, expand to be visible to the naked eye. In these conditions, particles begin to act as a single superatom, blurring the line between the individual and the collective. These quantum phenomena in space suggest that the universe is not just a place where things happen. It is a giant, participating medium that operates on rules far more complex than our daily experience of solid, liquid, and gas. Conclusion: the beautiful, unknown reflection on cosmic mysteries. As we journey from the fleeting, violent flashes of fast radio bursts to the gargantuan, reality-scarring threads of cosmic strings, a singular realization begins to take hold. The universe is far more dynamic, interconnected, and alive than the cold, static void we once imagined. We have looked into the heart of our own galaxy and seen the towering Fermi bubbles, the fading scars of a black hole's past hunger. We have peered into the deepest reaches of the cosmic web, where the very organization of matter seems to mimic the neural pathways of a mind. These phenomena are not just isolated curiosities, they are the brush strokes of a much larger masterpiece. Each mystery we have explored, whether it is the frame dragging of space-time around a spinning abyss, or the strange, frictionless superfluids inside a neutron star, serves as a reminder that our current understanding of physics is not a closed book, but a work in progress. We are like early map makers standing on the shore of a vast, uncrossed ocean, sketching the shapes of monsters and distant lands based on the ripples that wash up at our feet. What these phenomena tell us about reality. What do these cosmic anomalies truly tell us about the nature of reality? They suggest that the universe is governed by a profound oneness that bridges the gap between the unimaginably large and the invisibly small. The fact that we can use quantum mechanics to explain the internal glitches of a star 10 times the mass of our Sun, or use the geometry of a crack in the early universe to explain the lensing of light from a galaxy billions of light-years away, is a testament to the consistency of nature. However, they also hint at a deeper, underlying dark sector of the universe that we are only beginning to acknowledge. Dark matter, dark energy, and the dark flow that pulls at the edges of our observable horizon suggest that the normal matter we are made of, stars, planets, and people, is merely the foam on top of a much deeper, more mysterious cosmic ocean. Reality is not just what we can see. It is the interaction between the visible and the invisible, the known forces of gravity and the hidden tensions of the vacuum. The joy of not knowing everything. There is a unique kind of beauty in the unknown. In a modern world where information is often just a click away, the cosmos remains the ultimate frontier of genuine mystery. The fact that we still don't know exactly what causes an FRB, or whether cosmic strings are currently whipping through the room you are sitting in, is not a failure of science. It is the fuel for human curiosity. Science is often portrayed as a quest for answers, but its true heart lies in the pursuit of better questions. Every time we solve a piece of the puzzle, such as confirming that magnetars can produce radio bursts, we find 10 more questions hiding underneath. This joy of not knowing is what drives the next generation of astronomers to build bigger telescopes, and the next generation of physicists to rethink the laws of gravity. It humbles us, reminding us that we are a very young species in a very old and very complex universe, a call to exploration. The story of the universe is still being written, and we are the ones lucky enough to be reading the latest chapters. From the quantum fluctuations in the vacuum to the large-scale oddities that move entire clusters of galaxies, we are part of a grand, unfolding drama. If you have enjoyed this journey through the cracks in reality and the lightning of the cosmos, remember that the best way to support the continued exploration of these mysteries is to stay curious. Keep looking up, keep asking why, and join us as we continue to peel back the layers of the beautiful unknown. Don't forget to like and subscribe to join our community of cosmic explorers as we dive even deeper into the enigmas that define our existence. The universe is waiting, and there is still so much more to discover.